Welcome to this explainer on the system beneath. Today, we are diving into a hidden, honestly fascinating world. We're going to explore the incredible physical and software systems that keep our digital lives running smoothly, even when the actual power grid completely fails. We'll be tracing the exact sequence of events, all the way from a massive utility grid failure, right down to the software making split-second decisions inside a single server rack. So let's just jump right in. Picture this. You're just doing your normal everyday stuff. Sending a quick message, pulling up a cloud doc for work, or maybe you're streaming a video. Now imagine a massive thunderstorm rolls in and completely knocks out the high voltage utility power feeding the data center processing that exact action. Your lights at home might flicker or go out, but somehow your video just keeps playing. Why is that? How exactly does your cloud service survive when the massive building housing it goes completely dark? Here's our roadmap for today. We'll be hitting 5 sections. 1. The initial power loss. 2. Facility power continuity. 3. Backup generators and constraints. 4. Rack-level battery defenses. And 5. Geographic service failover. All right, section 1, the initial power loss. What happens when the grid actually fails? Now, you might think losing power is some rare, worst-case scenario. Well, actually, scratch that. It's super common. According to data from the Uptime Institute, a staggering 44% of data center outages are power-related. This can be triggered by utility disruptions, physical equipment faults like a random short circuit, or honestly, just general grid instability. Because the power grid is inherently unpredictable, data centers literally have to be engineered to assume it's going to fail. Moving on to section 2, facility power continuity, our very first line of defense. Let's trace the actual flow of energy using this schematic from the National Fire Protection Association. Up at the top left, you've got your normal utility power coming in. It passes through transformers and this massive switchgear. Right below it is the backup generator. Now notice how they both feed into that automatic transfer switch, or ATS. From there, the power flows down into the UPS, the uninterruptible power supply, which has its own little battery symbol, before finally reaching the load at the very bottom, which represents our servers. This handoff, it is rigid and it's completely automatic. Step 1, the utility AC power fails. Step 2, the UPS batteries instantly step in to take the load and bridge the gap. There is literally zero interruption to the servers. Step 3, the ATS detects that loss of utility power and activates. And finally, step 4, the ATS signals the massive diesel generators to start up so they can power both the servers and the facility's absolutely crucial cooling systems. Now, to be clear, according to NIST frameworks and IEEE standards, a UPS is simply a stored energy bridging system. It's definitely not meant to run the data center all day. It just provides conditioned power for a super critical 10 to 30 second window to meet strict recovery time objectives, or RTO, and recovery point objectives, or RPO. That 10 to 30 seconds is exactly how long it takes for a massive diesel generator to spin up, stabilize its voltage, and fully take over the facility's load. Which brings us to section 3, backup generators and constraints, the limits of physical power. Running a facility on backup generators brings some severe physical and regulatory limits into play. For instance, IEEE standards dictate that generator fuel supplies have to support continuous operation for a minimum of 12 to 72 hours. To put that into a real-world perspective, Stanford University IT notes that their technical facility generators have an average on-site runtime of about 24 hours. Plus, in the US, emissions regulations often cap diesel generator usage and testing to just 100 hours per year. And think about this. If a grid outage lasts for days, you are entirely dependent on the diesel supply chain. You're basically hoping fuel trucks can navigate through traffic in a potentially powerless city. So yeah, physical power has hard limits. All right, section 4, rack-level battery defenses, or how individual servers fight to survive. 100 million. That's a pretty wild number, right? Well, that is exactly how many lithium-ion cells Google Cloud has deployed in battery packs across its global data center fleet. And this isn't just one giant battery room somewhere. These batteries are distributed directly inside the server racks themselves. This means if a power distribution unit fails inside the building or a maintenance transition goes completely wrong, the servers can actually survive on their own local rack batteries without even needing the building's main UPS. Let's look at a really fascinating case study from Meta, a system they call the Power Loss Siren, or PLS. This timeline shows us exactly how long a single rack can hold on. At 0 seconds, the rack loses AC power, and those local batteries instantly kick in. The system waits through that 10 to 30 second generator startup window we talked about earlier. But if power isn't restored by the 45-second mark, the power supplies assert a hard signal.
imminent power loss. Why? Because by 90 seconds, those in-rack batteries are going to be completely depleted, and the physical servers will just die.
So what is Meta's software doing in that tiny, desperate window between 45 and 90 seconds? It kicks off an automated survival protocol. Step 1, a PLS relay on the rack switch detects the AC loss. Step 2, it fires off a UDP multicast alert to all the servers in that specific rack. Step 3, a PLS handler on each server hears the alarm and triggers the mitigation software. And Step 4, the server executes a graceful shutdown, hurriedly saving its data to disk before the battery dies. The hardware might be lost, but the data is saved.
And that leads us perfectly into Section 5, Geographic Service Failover.
This right here is the magic of how software completely outlives physical hardware. When Meta's Power Loss Siren goes off, their MySQL databases don't just sit there. They proactively promote a secondary database in a totally different data center region to take over as primary before that local server loses power. Meanwhile, their web servers immediately stop accepting new user requests, which drastically reduces error rates. Similarly, documentation from AWS and Google Cloud highlights how they rely on availability zones, which are entirely distinct failure domains. If one facility has a power event, user traffic is instantly and automatically shifted to a completely different facility miles away.
You see, the core philosophy of modern cloud architecture draws a really hard line between two concepts. Machine continuity is all about keeping a piece of metal powered up, using UPS bridging and local rack batteries. It's essentially a delay tactic. Service availability, on the other hand, is about the software seamlessly shifting user traffic to entirely different geographic zones. The physical hardware might die, but for the user, the service lives on. So we've traced this entire wild cascade, right? From a massive utility grid failure, through the automatic transfer switches and backup generators, down to the rack batteries, and finally out into the global software network. Which leaves us with this final thought. Restoring power is really only one stage of recovery. When the physical grid inevitably fails, is your service geographically designed to survive the dark? Thank you so much for joining me on this explainer. I really hope this structured walkthrough helped you see the incredible hidden systems working just behind your screen.